This is going to be 2 quick problems on buffers. I'm going to do, so out of those notes I gave you, the ones that look like this, do exercise 1 and exercise 4, just briefly in there. And again, I've put this key on Schoology as well for how to do these problems. But here's exercise 1. It wants to know the pH of a buffer that's made of 0.5 molar. This is called formic acid. Okay, so this is a weak acid. And if we mix that with 0.7 molar sodium formate, again, if we dissolve this, get rid of the sodium ions that do not affect pH, and you're going to have these. So this is a weak base. So we have a weak acid mixed with a weak base. You notice there's more of the weak base than there is the weak acid. So from the previous video, here's your equation. Remember, the Ka of an acid equals its H plus times the conjugate base over that. I've rearranged that to this situation. So pretty simple problem to do. The concentration of H plus then equals the Ka, so we need to know the Ka of this. Okay, and the Ka of formic acid is 1.8 times 10 to the negative 4th. Remember, this would have a Kb value, which you should be able to figure right now. If I took 1 times 10 to the negative 14th divided by this, that would be the Kb value of this. It's the conjugate base of that weak acid. So let's multiply this by 0.5 over 0.7. So this is the acid. That is the base concentration. We get a concentration of H plus that equals 1.29 times 10 to the negative 4th. Take the negative log of that, and your pH of this buffer solution is 3.89. Okay, so when these are mixed together in this ratio, the pH of that buffer is 3.89. You might wonder how the pH can be below 7 when we have more base than acid. The base is more concentrated than the acid. Well, the Ka value is much bigger than the Kb value of this. So it's a stronger acid than it is a base. Remember, if these two were equal, then H plus would equal Ka. pH would equal pKa. A lot of times when you're choosing a buffer, you choose based on this value right here. So let's say now, this was our initial pH, 3.89. Now I want to say, what happens if we add some hydrochloric acid to this mixture? Okay, so let's say that we add a little bit of HCl. And what they're adding is 10 milliliters of 1 molar HCl. So if we would add 10 milliliters of 1 molar HCl. So we're adding H plus ions in there. So if you think about what's going to happen, when we add H plus ions, it's going to react with the weak base. So as we add H plus ions from HCl, it's going to react with the CO2H negative and form HCO2H. It's going to form more of our weak acid. So adding H plus should make the pH drop a little bit. All right. As we do this, we want to do things in moles. Okay, we want to do this in moles. So this was molarity, this was molarity. All we need to do is get these into moles. Well, it said that you had a half a liter solution for these, and it was 0.5 molar, so we need to multiply that by 0.5, multiply that by 0.5, okay, to get those into moles. So, and then we need to say these are our moles of HCl. So our moles of HCl would be 0.01 liters times 1. So we have they're adding 0.01 moles of HCl or 0.01 moles of H plus ions. All right. Again, our initial ones of these would have been 0.5 molar times 0.5 liters. In other words, 0.5 moles per liter times 0.5 liters equals 0.25 moles of the acid. 0.7 times 0.5, 0.35 moles of the base. So whenever we're adding something in here, we're asking how much is there of the acid, how much of the base. So I'm going to use the same formula, concentration H plus equals the Ka, 1.8 times 10 to the negative 4th. I'm going to put the moles of acid and moles of base. So not concentration here, but moles and moles. Well, we initially had 0.25 moles of acid. We just added in 0.01 moles of H+. So I'm just going to add that and say, well, we added in 0.01 moles of H+. The base is going to react like we said with it. So the base is going to go down by 0.01 moles. So we're going to say we had 0.35 moles of the base originally minus 0.01 moles. It's going to decrease in concentration by that much. So when we do that, we get a concentration H plus of 1.38 times 10 to the negative fourth. Take the negative log of that. Again, that's your molar. Negative log of that, and you get your pH of 3.86. So adding 10 milliliters of 1 molar acid only dropped the pH from 3.89, which it was originally, to 3.86 for that buffer. The other one I'm going to do is number 4. You guys can do it. I'm skipping number 2. You don't need to know that one. But in number 3 you can do on there. But go to number 4. Actually, yeah, we'll do number 4. Number 4 in there gives you several buffers. So they want a solution with a pH of 4.3. They want to make a buffer with a pH of 4.3. Again, a good buffer is when we have equal acid, equal base. So typically to figure this out, if those are equal, that's 1. So that means the concentration of H plus equals Ka. If I take the negative log of that, that's pH equals pKa. So I can figure out if I take the negative log of the Ka, if I get those into pKa, I can figure out what the approximate pH of the buffer is going to be. So the ones that are on there, I'm not going to list all those out, but letter A is chloroacetic acid. If I take pKa equals negative log of the Ka, in this case 1.35 times 10 to the negative third. So the pKa there is 2.87. Well, we want pH and pKa to be equal, because when the concentration of H plus equals the Ka, then that's a good buffer. So we're trying to get one where the pKa is about 4.3. Well, if you do each of those, letter B, propanoic acid, if I take the negative log of that, you get about 4.89 for pKa. Letter C, I got a pKa of about 4.19. And letter D, I got a pKa of about 7.45. So the one that's closest to 4.3 would be that one. So if we made a mixture, so letter C, it's benzoic acid. If you mixed benzoic acid in equal amounts with its conjugate base, so you had equal of those, then you would have a pH of 4.19, so pretty close to 4.3. You could adjust that ratio to make it go to 4.3. You'd have to increase that compared to that. We'll get into that a little bit more.